Hello, I'm going to represent our final project reproducing a research paper in big data in healthcare field. So first of all, let me introduce a little background of this paper, which is improving medical code prediction for clinical text by incorporating online knowledge sources. So first of all, medical coding is a labeling process to translate patients' clinical notes to a set of standard medical codes. It's like a labeling process we usually do for the training data. And in the real world, it's very important because it facilitates the recording, tracking, and reporting of the patient's encounters. And for healthcare insurance company, the doctor have to fill the medical coding to get reimbursed for you. And medical coding is usually done manually by healthcare professionals, which is obvious, time-consuming and labor costly. On the left, we can see the average salary trend of a medical coder. And some techniques can do the medical coding automatically has been developed using a multi-label model. From those models, right now the model have the best performance. Usually are deep neural networks with attention mechanisms. Um, but there are still many challenges to improve such models. Of course, there will be some diseases are more common than other diseases, and definitely there will be some medical codes which are more common than the others. And that will lead to, we call it unbalanced training data set. That's the first thing. And the second thing you can see from the clinical notes is that usually the clinical notes, they will have just very short sentences, less than maybe a couple hundreds of words, which would be too short for the model to catch its features, even with some attention mechanisms. And that would be the major one of the major challenges right now to improve such automatic medical coding models. And our paper trying to reproduce develop a new kind of technical framework called knowledge source integration framework. And this technique basically is to use for example, like Wikipedia and math-based data here, and you will get a bunch of more tests for this medical codes than the original clinical notes. And in their paper, the results show that it works. Their point is that it can improve the accuracy for the rare codes. For example, the label frequency is less than 1 to 10 and 11 to 50. And that's a very important point they're making here. So the original paper also claimed that the KSI method does not only improve the accuracy, but also improve the interpretability. But we not evaluate the model interpretability due to our lack of medical knowledge. The framework can be decomposed into two parallel subtasks. The first subtask is the traditional multi-label classification, and the second subtask is document similarity learning. First, it represents the document KI into vectors xi and the clinical nodes n to vector q, and then it performs element-wise modification of si and q to obtain their intersection vector z, and as it projects z to a low-dimensional vector e, and then if it is enabled, the attention mechanism is used to transform e to a weight vector vi. Finally, we will project vi into a similarity scope, and they will combine this kind of two vectors to get a final output. And the model we are using is similar to the original paper. We use INN. Basically, it's a very simple baseline INN models. And with the attention mechanism, we only just apply the attention score instead of the mass pooling layer and add a bias term. And similar things happen to the CNN as well. I would like to say it's a very standard kind of a baseline CNN model. So the raw data we are using is for Mimi3 database. Our label is 941 unique ICD codes, and like we said, 400 of codes account only for 1% of the occurrence, which are the rare code we are implicating. And the input is 50,000 clinical tags, and our KSI framework is using the external knowledge from Wikipedia, which is basically like 325 documents, and 109 of them are for those 400 rare codes. And we process the raw data in 3 steps. First, we need to get the vocabulary from the nodes, and then we need to do the intersection between the vocabulary and the wiki page. And we split the dataset into 70% for training and others for validation and testing. And we use PyTorch package to run the model. The original codes were provided by the authors, but we actually made some changes to make the model running more efficient, more effectively. So in this study, we test all 4 kinds of models, and for each model, we compare its performance between the baseline version and the KSI version using 6 evaluation metrics. Test loss is the average of the binary cost entropy loss over all the test nodes, and the top 10 recall is calculated as the number of correctly predict medical labels over the number of total medical codes for that node, and then average over all the test nodes. And we use different kind of AUC and F1 here. So the macro metric is calculated for each medical code itself, and then average is taken over all the codes, while the micro metric is calculated for each node, like the input data, and then the average is taken over the nodes. So therefore, the macro metric weighs the rare medical code the same as the frequent medical code. As shown in the table, yes, the KSI framework indeed can constantly improve all kinds of deep learning models. Almost all the KSI model performs better than the original, the baseline model. And like I say, the macro measures will evaluate the rare medical nodes more on the rare medical codes. And you can see that the improvement of the macro measures are actually more obvious than the micro measures, which prove the claim of the original authors that it will improve the accuracy more on the rare medical codes. So the KSI framework can indeed improve all kind of model performance, but I would say we need to observe more diverse models, and actually the improvement are very minor, although it's universal improvement for all kind of model. And the easy part of this research is the model training and the evaluation part, but we didn't do the model interpretability because it will take a lot of professional medical knowledge to do that. And that's all the efforts we have done to reproduce the result of the original paper. Thanks for watching.